Yep, there we go. Hit record on the screen recording, and we'll go ahead and get started here. So we have problem 1, amoeba in a dish. It says an amoeba is in a petri dish, and it's crawling initially with a velocity vi of magnitude 12 micrometers per second, headed due south. It makes a turn and slows down slightly over a time interval of 6 seconds, giving a new velocity vf of magnitude 5 micrometers per second headed due east, right? So we have a initial velocity component and a final velocity component, and they're giving us the magnitudes of each and then the directions as well. So part A here says on the diagram, sketch and label both vectors and sketch the change in velocity vector delta v, right? So if I think about it, delta v, like they pointed out here, is vf minus vi. So if you've kind of like looked over the first couple of slides, or if you attended lecture, then you know that for vector addition, the way we add vectors together is the tip to tail method. So that's, if you have like an arrow like this is a vector, let's say this is vector A, right? And I want to add it to vector B. So I would have a tip to tail method, so I get the tip here and add that to the tail of the next vector, right? Let's say this is vector B, vector A, and this is vector B. And that would give me a resultant vector C, which in order to find that, it would just be, from here, from the tail of the initial vector to the tip of the final vector. So then I would have, let's do a different color, vector C as my resultant vector. And so C is equal to A plus B. Now, if I said I wanted to subtract B, right? Subtracting B, A minus B, all that's saying is that you're adding the inverse of B, basically, right? So that just means that I'm just going to take, whatever direction B was in and then flip it. So if it was north, then B is going to be south, right? If A was like northeast, right, then roughly A would be southeast if I were to flip it, make it negative A. Or southwest, my bad. Southwest. So that's generally how we're supposed to add vectors, right? So if I was thinking of delta V, Vf minus Vi, right, then first of all, I have some initial velocity, right? That's going, initial velocity 12 micrometers per second headed due south. So I have a Vi this way, south, and then Vf headed due east. So you would think that it would look like this, right? But in reality, this is Vi plus Vf, because what this is doing is tip to tail method, right? I'm putting the tail, right, of Vf to the tip of Vi. So what this would be is Vi plus Vf. So the question here is how do I get it to Vf minus Vi? Well, Vf is the positive, right? So if I want it where it's minus Vi, then technically I have to flip Vi here, right? So if I flip it from south to north, basically, right, then it would actually look like this. Vf, which is positive, and then I would have to add the inverse of Vi, right, which would be negative Vi, and that would be north instead, right? If this is Vi plus Vf, right, because I go by the original directions, this is south and this is east, right? They said headed due south, and then Vf is headed due east. So if I need to flip Vi, right, because otherwise I would have it be Vi plus Vf, because this is tip to tail method, right? If I want to make this negative Vi to where it's Vf minus Vi, then I have to take the direction of Vi and flip it. So I have to make it go from south to north, right? So, and then delta V would just be the resultant vector, which would just be, like I said, from the tail of the first vector to the tip of the second one, right? So if I were to take the resultant for this one right here, which is the correct one, delta V would look like that. So delta V would be this, right? So if I want to sketch this on the graph, first of all, I have to indicate that VI goes south like this. VF, right, goes east like that. Now, this VI, like I said, is going to be flipped from south to north, right? So if I want to add that, if I want to do VF minus VI, I have to flip it to where now VI is like that, right? Because this isn't, if you think about it, this isn't like proper tip to tail addition, vector addition, right? If it was proper, then it would look more kind of like this. And say if I want to do VF plus VI, then it would kind of look like that. And so there you can see that if I want to do VF minus VI, I just take this and then I flip it up above the x-axis to where you get VF plus the inverse or the negative of VI. All right, does that make sense? Yes. How about you, Lydia? Does that make sense so far? Mm-hmm. Okay, cool. But do you understand like all of the vector addition stuff? So is this making sense to you now, hopefully? Okay, awesome. So yeah, that's how your sketch should look like basically, where it's VF, right? That was east, that's always east, and that's what we keep the same because it's positive, right? Now we add the inverse of the original direction, which if that was south, then we make it north, and then we do VF plus the inverse of VI, so VF minus VI, and then we draw the resultant vector from the tail of the first to the tip of the second. So our final direction, our delta V, should look kind of like that. So moving on to B, it's asking us to find the x and y components of VI and VF and use these to calculate the components of delta V, right? So for VI, they said we had a magnitude 12 micrometers per second headed due south. So if it was headed due south, right, it's not southeast, it's not southwest, right? It's not at an incline, or it's not at a specific degree or anything like that. So our x component would be what for VI? For the x component? Yes, my bad. I was thinking y component for some reason. Yeah, you're absolutely right. I was thinking for VF for some reason, but yeah, 0 micrometers per second. You're absolutely right. And then y component for VI is going to be what? Right, so that would be the magnitude of it, and then we need to also assign a direction, right? So it was 12 micrometers headed due south, and then if we just go by the regular old coordinate plane directions, right? So this is positive y, this is negative y. So, and we're going obviously by the original direction of the problem, right? So we're doing VI headed due south. So if it was south, it was in the negative y direction. So it should be negative 12 micrometers per second. Now for VF, the x component, we have 5 micrometers per second headed due east. So that would be 5 micrometers per second for the x component. And then for the y component, since we're only headed due east, there's no direction in the, or nothing in the y direction, right? Then we don't have a component for that either. So 0 micrometers per second there. Now it's asking us to calculate the components of delta V. So we have, that would be like delta Vx, right? And delta Vy. So for delta Vx, that would be equal to Vfx minus Vix, and this would be Vfy minus Viy, right? So that means taking Vfx, right? So that was 5 micrometers per second minus the initial velocity in the x direction, which was 0. So this should be 5 micrometers per second minus 0 micrometers per second. How about delta Vy? What would we have for this part? Right? Yeah, so we'd have your Vfy, your final in the y direction, and 0. And then we subtract it from the initial in the y direction, which was negative 12. So 0 micrometers per second minus negative 12, right? That should give us 12 micrometers per second for our delta Vy. And our delta Vx is going to be 5 micrometers per second. So delta Vx is 5 micrometers per second. Delta Vy is 12 micrometers per second. So that's basically the gist of part B. You're figuring out the initial x and y components for the initial velocity and the final velocity, and then we have to then figure out the x and y components of the change in the velocity. So that's basically saying, okay, well, we have Vf, that was solely in the east positive x direction, so that's only going to have an x component. Vi, based on the information in the problem, was headed due south. That was only in the negative y direction, right? So there's no x component there. And then, right, we have to figure out the delta V components in both the x and y directions, which delta V components are just going to be Vf and Vi because they're both in only one direction. So they're not like this way or that way or anything like that. They're either east, north, south, west. They're firm directions. And so you don't have to calculate anything with like regards to angles or anything like that. We'll get into that later, but that's basically part B. Make sense? Make sense, Lydia? All good? Okay, cool. Now we can move on to part C. So we need to find the magnitude and direction of delta V. So to find the magnitude of delta V, that's just going to be what? So we have delta V here. This is a triangle, right? How can we figure out the value of delta V? Because we have Vf, or my bad, Vx and Vy, right? So let's change this up a little bit to say Vx and Vy, and then we have delta V, right? So if we have those two values, Vx and Vy, and we have delta V that we need to figure out, how can we figure out the value of delta V? Pythagorean theorem, right? So delta V is just going to be equal to, or let me actually, you know what, write it out a little bit fuller. So if I say delta V squared equals Vx squared plus Vy squared, right? So that's saying like c squared is equal to a squared plus b squared, right? That's the same kind of format there. So in order to figure out delta V, we just take the square root of the whole thing. So we can get delta V is equal to the square root of Vx squared plus Vy squared, right? So in that case, whether you have a negative sign or not, it's going to be canceled out by the square, because if you have like -4 squared, that's going to be 16. Regardless if you have a negative here as your value or not, it's always going to turn out positive because you have the exponent squared, right? Now, that is going to be helpful because we're trying to find the magnitude, so we don't want any negative signs. We only want the absolute value of everything. So magnitude is just going to be the values without any indication of direction. We're going to give the direction later on here, so we'll figure that out. But for now, we just want to figure out the magnitude. So if we take Vx squared, so we know Vx was 5 micrometers per second, we can square that, and then we have Vy squared, that was 12 micrometers per second. So we can square that as well, right? If we add the two together, 5 squared plus 12 squared, square root the whole thing, what do we get? Yep, 13 micrometers per second. Yep, absolutely right. So 13 micrometers per second, that's going to be the magnitude of delta V. Now we need to find the direction, right? So in order to find the direction, the way we do that for these types of problems is via an angle, and then like a cardinal direction. So we can say, like, if you ever heard, I guess saying, for example, like, oh, the direction is 50 degrees east of north, or 30 degrees west of south, or something like that, right? So that's how we're going to define or, say our answers, basically, or how we're going to put down our answers. So we'll have some kind of degree, some kind of angle, and then a cardinal direction. So in order to find the angle, right, it can either be this angle here or that angle there. So it could either be between the vector itself and the y-axis, or the vector itself and the x-axis. Now, it doesn't really matter what direction or what angle you pick, as long as you get the angle, you get it calculated correctly, because the two angles will actually be different, right? There'll be different values, but once you get the angle, you also have to match up the angle with the proper direction. So this direction here, right, between the vector and the x-axis, right, that's going to be, if this is east, right, this is east, and obviously this is north, right? So imagine the vector here starting on the x-axis and then slowly moving like this. So this would be some degree, so let's say like 30 degrees north of east, if we were to use this angle right here. Now, if we were to use this angle right here, sandwiched in between the y-axis and the vector itself, then we have to start here and pretend as if this vector went like this, this, east of north. So, kind of as a fill in the blank kind of exercise. So if I have the angle sandwiched between y-axis and vector, then I say this is the y-axis direction, and then this is the direction that is for V. So basically what this means is, so I can put like blank of blank, right? That's how I'm going to describe my direction. So if the angle is sandwiched in between the y-axis and the vector, then I start off with like the vector's direction, so it's east of the direction of the y-axis. So if the y-axis is north, then I just went east of north if I'm sandwiched between, if the angle that I'm looking at is sandwiched between the y-axis and the vector. Now, if it was sandwiched in between the x-axis and the vector, right, then I go with the direction of the y-axis, or my bad, the direction of the vector, right, and the x-axis second. So what this means is if I have the angle here that I'm looking at, I start off by saying, okay, well, this vector is north of the x-axis. So this is north of east. So if the x-axis is east, then I go this way to reach the vector, and so that's in the direction north of the eastward direction. Does that make sense? Yes? Okay. So just as another example, if I had this vector right here and I wanted to look at this angle, then what would the direction be? So the vector was located here, and I'm looking at this angle, sandwiched between the y-axis and the vector. Yep, west of north. Awesome. So there you go, we got it. So if you kind of follow those little fill-in-the-blank kind of guidelines, that'll help you out to kind of figure out how to describe the directions. Some people have more trouble with it than others, but if you kind of get the gist of the difference between these two angles, you're good. Anyway, in that case, right, we can just pick whatever angle we want to look at here and then go from there. So let's do east of north. Doesn't really matter which one you pick, but I will do east of north. Right, so this is this one right here. So if I want to figure out that angle right there, right, then how can I figure that out using the trigonometric principles that I know? So like think of sine, cosine, tangent. I know that Vx is 5, Vy is 12, right? How can I figure out this angle here? And the way you can imagine it too is if this was Vx, and this is Vi as well. Or Vy, my bad. So this is Vx, this is Vy. How can I figure out this angle? Yep, excellent, inverse tangent. So if I take inverse tangent of Vx, right, because this will be opposite over adjacent, which is tangent. So if I take inverse tangent of Vx over Vy, right, that'll give me the theta, or the angle that I'm looking for. So I take inverse tangent of 5 micrometers per second over 12 micrometers per second. That should then give me the angle that I need. And so let me know what you guys get for the angle. $22.6 degrees. Lydia, did you get that as well? 22.6 degrees. Yeah, that's about right. Yeah, 22.7, 22.6. Just kind of depends on your rounding. And yeah, it looks like you might have done the other angle, and that would be Vy over Vx. So that would have been like 12 over 5, and you would have to subtract 90 from this one. But yeah, so 22.6 degrees east of north. Or Lydia, what you got was 67.3 degrees. I think that's what you got, right? So yeah, that would be like 67.3 degrees north of east then. Either one will work. The professors will accept either answer. As long as everything's consistent, like your calculations are consistent with your directions, with your degrees, with all that, you're fine either way. So either option is acceptable. Just kind of depends whatever one is easier for you to kind of figure out. Because I know this angle might be a little bit more difficult to kind of envision because you have to draw out Vx here over Vy, as opposed to Vy over Vx, which was kind of given there. But yeah, either one works. Sound good? Okay, cool. So now for part D, we're trying to figure out the magnitude and direction of the average acceleration during the turn, right? So first of all, we can kind of write out average acceleration. Oops. This is average acceleration, and then we need to find the magnitude of it, so that just indicates that we're taking the absolute value. We want just the value itself, no indication of direction. So we want the magnitude, and then the direction, we'll kind of add that with the direction that we got from part C, which was the 22.6 degrees east of north, or the 67.3 degrees north of east. So we know that average acceleration is equal to delta V, and this will be, once again, an absolute value of delta V because we don't want any indication of direction. We just want the magnitude, and that's over delta T, right? So if we want to find the average acceleration, we take delta V over delta T, and then, yeah, that's it. So delta V, we already stated that was 13 micrometers per second in part C. So we just take 13 micrometers per second, and then the time elapsed was 6 seconds. So it says time interval of 6 seconds. So it says makes a turn and slows down slightly over a time interval of 6 seconds. So we have 6 seconds as our time interval, and that should give us what for our acceleration? Yep, around 2.2. I had around 2.17 micrometers per second squared. 2.2, if you want to round it, go ahead. I personally don't round a bunch, just for the sake of having like the most, like, I guess, accurate answer. But yeah, if you want to round it, because it's 2.17, if you round that, it's 2.2, so either way, doesn't really matter. But yeah, around 2.2, 2.1 should be the right answer there for the average acceleration magnitude. And then we can say as well that it was 22.6 degrees east of north, or the 67.3 degrees north of east. But yeah, sound good for problem 1? Any questions at all? So that's a great question. So I know that it's one of those things that's really, really weird. Let's say, like, in reality, right? If I were to draw this out, velocity VI headed due south. So if this was literally just like, if this was like your Google Maps route, right? Then I moved south like this, and then I moved east like that, right? So technically, it should be in the fourth quadrant. Like, you're not wrong. Like, you're not crazy about that, not one bit. But in terms of portraying our change in velocity, we have to basically add the inverse of the initial velocity vector. And so the only way to do that basically is kind of, oops. So if I had, this was VI and this was VF, right? Then the only way to do that is if I can flip VI like that. So where it goes from south to north. But in that case, then what your graph looks like is something like this, VI, and then that's VF. And that's not right because this isn't like the tip to tail method. So I would have to kind of, move it around a little bit to where it is like that, right? So in that case, your graph should yeah, it's just the fact of the matter that we have to calculate the velocity. It's not an actual matter of like the direction that you were going in or anything like that. But I guess, let's see here. So I do south, takes a turn, slows down slightly over time, interval 6 second meter new velocity, headed due east. Yeah, this one is it's very weird how they want you to figure things out, but I mean, if I were to think about it, yes, like you said, I'm going south and then I go east. But I guess it's just more of the nature of that we need to figure out the change in velocity. And so this is, I guess, the change in the velocity vectors or the direction of the change in velocity is what we're figuring out here, not the actual like final direction of where the amoeba is, if that makes sense. You see what I mean? Yeah, yeah. Mm-hmm. Because remember, like here we're looking at acceleration, right? So if it's slowing down, right, there's some like acceleration has to be moving or directed in the opposite direction as velocity. So if I was, say, for example, if you were only doing like 1D motion, if I was just going on an x coordinate left or right, if I was moving this way, positive velocity, for example, if I'm slowing down, then acceleration has to be in the negative direction or the opposite direction, right? So, like, I could still very well be moving in the east direction, but I'm slowing down because acceleration is the negative direction. So when they ask us to find delta V here, and then obviously at the very end divided by time, it's only a matter of like figuring out the direction of acceleration basically. And so that's why your direction here is a little weird and it's not indicative of the actual direction of the amoeba, like its final direction. It's just indicative of how the velocity has changed over time basically. Sound good? Okay, cool. Because I know, yeah, it's really weird how they just don't kind of give like a explanation of that basically. But yeah, that's just it's just trying to figure out like the direction of the acceleration basically. Because if you take this delta v over delta c, you get your acceleration. Otherwise, you're absolutely right. The final actual position of the amoeba should be somewhere down here theoretically. But yeah. Hopefully everything else makes sense for problem 1. Okay, awesome. Problem 2, very similar idea, but we're kind of elevating it a little bit. This one is a little bit more difficult just because the drawing is a little bit annoying to figure out. But basically it says a goose flies 40 miles at a bearing of 30 degrees east of north, and then turns and travels 25 miles at a bearing 80 degrees west of north. Right? Now, here's the thing. It gets very complex when you change directions and you go at a different angle. So for that second distance that it travels, right, the 25 miles at a bearing 80 degrees west of north, that's where it gets more difficult. But for part A, they want us to sketch the goose's trajectory starting from the origin. So we have to sketch the first displacement as a vector from the origin, then sketch the second displacement as a vector starting at the tip of the first vector. And then take east to be positive x, north to be positive y. And then we have to sketch the goose's total displacement vector. So, that being said, if it was traveling 30 degrees east of north first, right, then east of north should be like this angle that we're referring to, basically, right? This is north. If we go east of north, then this is the angle that we're referring to. So you can essentially kind of draw it out like this, more or less. That looks more like a 45-degree angle, but let me try that again. Yeah, whatever. We'll just say this is 30 degrees for the moment. And then, good tip for drawing stuff in physics. Try your best to draw it out the first time correctly, but if you need to kind of adjust it as you go along, that's totally fine. So, number one thing is to make sure like your calculations make sense. And then if your picture doesn't make sense with your calculations and you know your calculations are correct, you can kind of adjust your picture to match the calculations. Like you might need to shift the line upwards like this or something if the final direction of the vector isn't 100% correct, but you can always try your best and kind of go from there. So yeah, we first go 30 degrees east of north, and then we want to go 80 degrees west of north, right? So this second part here is where it definitely gets very confusing, because basically they want us to do west of north. So if it was west of north on the normal coordinate plane that we see here, then it should be this like angle there, right? So if we wanted to draw 80 degrees west of north on this coordinate plane here, it would look kind of like this, because this whole thing would be 80 degrees, and this little sliver here would be 10. So 80 plus 10 is 90. So what we want to do is kind of like draw a makeshift. Actually, let me try to do a dotted line here so it looks better. Is draw kind of like a makeshift coordinate plane, right? There we go, something like that. And so then you had to kind of do the same thing that we did over here, where we said, okay, well, this is 80 degrees. So then we look at this as the y-axis, this is the x-axis, and then kind of draw it again. So this is the only trick really to drawing it properly, is that you kind of have to draw your own second coordinate plane right there to figure things out. So if I wanted to draw 80 degrees west of north, it would look kind of like that, to where this is 80 degrees right here, and then like I said, that little sliver right there is 10. But then the hard part is over, right? We need to then figure out our final resultant vector, and like I said, that the resultant is drawn from the tail end of the first vector to the tip of the final vector. So it should look close to this, right? If this was our A vector and this was B, this would be C. A, B, C, there. So that should be what your drawing looks like for part A. Sound good for the direction? Is this because of the tip to tail method? Is that why we draw B on top? Yeah. So tip to tail, because it goes, here's your tail, here's your tip, and then the goose traveled 25 miles at a bearing 80 degrees west of north. So then your tail of the second vector should be connected to the tip of the first one. So you just have to draw for that second vector, since you essentially change up directions, because you were traveling at 30 degrees east of north first, and then all of a sudden you want to go 80 degrees west of north. So when you change up directions, you kind of have to draw your own second coordinate plane to adjust for that new angle, and then obviously you will add it tip to tail. Make sense? So it'd be normal just as like a basis to draw normal way on the original coordinate plane and then reflect it. So yeah. So like I said, you can draw it first on the original coordinate plane to kind of figure out how it needs to look, and then kind of imagine it as, okay, let me just take this thing and then bring it up here, right? So it's as if I just went like this. Okay, this is 80 degrees west of north, and I just went and dragged it up top here. That's it, same idea. But yeah, if you want to do it that way as well, that works to kind of help you envision it a little better. But I just prefer to draw like an entirely new coordinate plane up here, and then imagine this is the y-axis, this is the x-axis, and then draw it from the tip here and onwards like that. Make sense? Okay. Yep. Make sense, Lydia, as well? Okay, cool. So now we have to find the x and y components of the Goose's total displacement vector over the flight. So the total displacement vector is, or what vector basically represents our total displacement here? C, right? Yep. So C would be our displacement vector because it gets us initial to final. Final, initial, right? So if we want to find out Cx and Cy, right? Well, we know that C, based on vector addition, should be equal to A plus B. So C is equal to A plus B, right? So Cx is equal to Ax plus Bx, and Cy is equal to Ay plus By, right? The A and B components for x will give the x component for C, and the A and B components for y will give the y component for C. So this is just a matter of figuring out Ax and Bx, Ay and By via trigonometry, right? So we have an angle of 30 here. We know that A is 40 miles and B is what, 25 miles? Oops. 25 miles. So then we can just use trigonometry to figure things out. So this is why I said drawing a second coordinate plane would be helpful, because then you can kind of look at this as bx here. Let me get the dotted line again. This is bx basically because that's in the x direction, and this little part right here, so this is, let me make it a little bit smaller, by, and this is bx. Or let me, actually, you know what, I'll just do it in a different color altogether. This is bx, oops, by, and this is bx, right? So this is bx, this is by, right? Because this is the x direction, this is in the y direction. And then we also have ax and ay, right? Or alternatively, you can also say here, well, kind of cuts it off, but this is ax and this is ay as well. Ax and ay, because then you can really easily look at that angle there without having to calculate this one to figure out these components right here. So if we wanted to find out, let's start off with A first. So ax is unknown. I want to figure out ax. How can I figure out ax from the angle that I have and the value of the overall vector there? Yep, 40 sine 30. So we would use sine because sine is going to be opposite, so ax over hypotenuse, 40. So ax over 40 is going to give us sine 30, right? Opposite over hypotenuse. And then, yeah, ax is equal to 40 sine 30, which then is equal to what? I think that's around 20 miles, I believe. Let me know if that's what you guys got as well. Okay, cool. And then we have AY is equal to what? Yep, 40 cosine 30. Awesome. So yeah, AY over 40, so that's adjacent over hypotenuse, right? Adjacent over hypotenuse to this angle right here. AY over 40 is equal to cosine 30, and then AY is equal to 40 cosine 30, sorry. 40 cosine 30, and then that's equal to around, 34.6 miles. So there's AX and AY. Now we need to figure out BX and BY, right? So BX here's BX, and here's that little angle, 80 degrees. So how can we figure out BX? And we know that B is 25 miles. Yep, so we're going to use sine again, right? So BX here, opposite to this angle, 80 degrees, opposite, over hypotenuse, which is 25. So BX over 25 is equal to sine 80. BX is equal to 25 sine 80. And then that should give us, what, 25 sine 80 is around 24.6 miles. Now, the key here is, since this is in the western direction, right? They said that positive x is east. So if this was west, then what do we have to add here? Yep, exactly, negative. So negative 24.6 miles because you're going west, right? And then for BY, what do we get for BY? Yep, so 25 cosine 80, so BY over 25 equals cosine 80. And that's because we have this BY here is adjacent to the 80 degree angle, so adjacent over hypotenuse, BY over 25 equals cosine 80. And then BY is equal to 25 cosine 80. And then that's equal to around 4.34 miles, I believe. Sound good so far? Okay, cool. So we have AX, BX, AY, BY. So then this is just a matter of adding things together. So AX plus BX, 20 miles, plus negative 24.6 miles. And then this is AY plus BY, so 34.6 miles, plus 4.34 miles. that gives us Cx equal to what and Cy equal to what? I got negative 4.6 miles for Cx, and for Cy I got 38.98 miles roughly. Let me know if that's what you guys got as well. I got you, I see. Yep, no worries. But yeah, that should give you Cx and Cy, and that's your x and y components of that total displacement vector. And you can see here that you can do kind of like a sanity check and see if your answers make sense. So you should have your Cx be negative 4.6 miles and your Cy be 38.98 miles, right? So you can see that here it's definitely in the negative x direction for that C vector, and it's way up high here, almost 40 miles, right? And you can see here as well that it's roughly the same length as that A vector. So everything from our drawing and our calculations makes sense. So then, kind of move on to C. It asks us if the Goose's flight takes a total of 1.5 hours, find the magnitude and the direction of the Goose's average velocity, right? So we know that average velocity, if we want to find the magnitude of that, you can take the absolute value, and that's equal to our delta x over delta t, right? Let me actually adjust this a little bit. There we go. So the delta t we know is 1.5 hours. Delta t is 1.5 hours, right? We need to find the delta x. How can we find our delta x? Remember, our delta x, which is our total displacement, should just be the c vector here. So if we want to find c, how can we figure that out? Yep, Pythagorean theorem. So we have, from part B, we knew that we have a value for Cx, and we have a value for Cy, right? So we know that a squared plus b squared equals c squared for the Pythagorean theorem, right? And that could be cx squared plus cy squared equals c squared, right? So we just take the square root of the whole thing, and we're left with cx squared plus cy squared. Square root of the whole thing is equal to c. Oops. There we go, c. And then we know that our c is technically our displacement vector, because that's what they said here in part B, where the Goose's total displacement vector is modeled by this vector c, and then we figured out the x and y components of c. So taking cx squared plus cy squared, square rooting the whole thing, gives us c, and that gives us our delta x. So we should do square root of cx, which was negative 4.6 miles squared, plus 38.98 miles squared. I'm forgoing the units at the moment just to save some space. But yeah, these are in miles. And then we take the square root of the whole thing. That gives us our c, or our delta x. And putting in the negative or leaving it out doesn't really matter, because like I said, if you do negative 2 squared, that's going to be 4. If you do 2 squared, that's going to be 4. If you take negative 4.6 squared, that's going to be the same as 4.6 squared, because of that squared right here. If you multiply two negatives together, it gets a positive. So it doesn't really matter if you add in the negative or not. The most important thing is that our delta x here should not have a negative value there, because we only want the magnitude at the moment. The direction, as usual, with the previous problem as well, the direction is going to be indicated with an angle and some kind of cardinal direction. East of north, north of east, whatever it is. So that being said, for delta x, what did you guys get? Or see, basically. $39.2. I got 39.3, but rounding errors and different calculators will account for small differences here and there. But that doesn't matter. This class doesn't factor in any like significant figures or any of that, and they don't really bog you down too much about rounding and all that, as long as everything is kind of pretty close to the correct answer and within reason. So as long as your work is correct, if you have, say for example, like if you mess up the final answer for whatever reason, but all your work is correct, you're going to get points for all of your work, and then you might just get like a point off or half a point or whatever it is for having the incorrect final answer. But yeah, 39.3, 39.2 is about right, and that's miles. So that gives us our delta x, 39.3 miles divided by 1.5 hours, and that should give us our average velocity, and that should be around 26.2 miles per hour. Let me know if that's what you got as well. Yeah. But yeah, 26.2, 26.1, about right. And then we finally just need a direction to indicate our direction. Or, yeah, we need a direction. We need an angle to indicate our direction. That's what I meant. So, if we want to figure out an angle, we can either do this one or that one. Do you guys want to do west of north or north of west? Once again, it really does not matter at all. I've already done north of west, so we could do that one. Or if you guys want to kind of change it up and get the west of north answer, doesn't really matter to me. I'm sorry, I couldn't hear you well. Did you say you wanted to do the west of north one? Or the north of west, I mean? Or wait, hold up. West of north, gotcha. Okay, west of north. So west of north, right? We have, you can kind of draw it out here like CX, and this is CY. So we're going to be taking, like that previous problem, I'm going to be taking the inverse tangent, so opposite over adjacent, CX over CY, right? So inverse tangent of CX over CY, and we know CX is the negative 4.6 miles, but we don't want to have any negatives when we're calculating our tangent, or like when we're calculating our angles. I just prefer to have like the magnitudes there, because if you have negatives and you try to indicate direction, it'll just mess up the angle that you're going to get. So I just put 4.6 miles for CX, and your CY, you're going to get 38.98 miles, right? And I don't have this one calculated out, but I'm just going to subtract from the answer that I have for north of west. You should get around, what, 6.7 degrees west of north. Okay, cool. So yeah, 6.7 degrees west of north, or around 83.3 degrees north of west. And do a sanity check, 6.7 degrees plus 83.3 degrees. That should add up to 90. So you can imagine west of north, this would be, I kind of drew it a little bit inaccurately, but this should be kind of more inclined like that way. So this is a really small sliver of 6.7 degrees west of north, and then this should be a really big 83.3 degrees north of west. But does that make sense overall? Any questions about the direction or the angle or any of that? Yeah, okay, got it. Okay, cool. Okay, for part D now, it's asking us what's the average speed. So speed instead of velocity, average speed, right? So speed is equal to what? What is the definition of speed, basically? Distance traveled over time, right? So sometimes we'll put L as in like path length over time, or you can do like a little d over t like that. Doesn't really matter how you portray it, as long as you don't put like a delta x, because delta x is indicative of displacement. So yeah, L or d over delta t, right? Total distance over total time. So we know our time was 1.5 hours from before, but what's our total distance? How can we calculate that out? Yep, excellent, awesome, great job. So yeah, absolutely add up the 40 and the 25 because that's your path length, right? Because think about the whole displacement versus distance thing. I could go like this and end up here, right? Displacement would be from here, this initial position, to there, but my path length would have been this whole deal here to get to the final position. So in order to get to here, my final position, my displacement was the c vector, which was from initial to final, but my path length was, okay, I went from here to here on the vector A, from here to there for vector B. So yeah, 40 plus 25 miles would give us our total distance traveled. So that's 65 miles over 1.5 hours. 65 miles over 1.5 hours. And that should give you around 43.3 miles an hour. Sound good for part D? Yep. Okay. Now for problem 3, if you guys are all right to move on now. This one is once again kind of a repeat of what we did for the previous problem, but we have, okay, it says we have 3 players on a reality TV show. They're brought to the center of a large flat field. Each is given a meter stick, a compass, a calculator, a shovel, and the following 3 displacements in order: 72.4 meters, 32 degrees east of north, then 57.3 meters, 36 degrees south of west, and then finally 17.8 meters due south. The 3 displacements lead to the point in the field where the keys to a new Porsche are buried. 2 of the players take the brown path, following the 3 displacements in order. However, the winner calculates the net displacement of all 3 vectors and follows the blue path, getting there faster than the other 2 contestants. Well, he probably took this class. He knows physics, so that's why he did well and calculated displacement. Sucks to be them, those other 2 players. But that's kind of what we're going to be doing for all these parts, figuring out all the components for A, B, and C, and figuring out the resultant vector as well. So for part A, and here, like I said, unless they specifically state that they want it to be rounded to some decimal place or whatever, it doesn't really matter if you round or not, as long as the answer is pretty close. But in this case, they want us to round to 2 decimal places for each value. So part A, the winner already calculated some components correctly, saving you some work. AX is equal to 38.37, AY is 61.4, CX is 0, and CY is negative 17.8. So we need to calculate BX and BY. So this is our BX right here. This is along the x-axis. This is our BY along the y-axis here. And then we have this angle here that's 36 degrees. Oops, 36 degrees right here. So once again, we're just going to be using our trig functions, right, to figure out bx and by. So bx is equal to what? How can we figure out bx? This is the angle here, and this is bx, and this is 57.3. How can we figure it out? 57.3 cosine 36. Sounds about right to me. So that's bx, right? That's your adjacent. And then over hypotenuse, which is 57.3. Bx over 57.3 meters is equal to cosine 36. Bx is equal to 57.3 cosine 36. And then, absolutely right, this should be a negative answer because we're moving west in the negative x direction there. And this should be around negative 46.36 meters, if I'm not mistaken, for bx here. Let me know if that's what you guys got as well. And then I will set up by. Okay, awesome. Negative 46.36 meters for bx, and then by will be a similar thing. We just have to use a different trig identity. For by, so by went from, when we go to from B to C, we're traveling south, right? You see what I mean? So yes, it is in the positive quadrant, but since we're moving south, yeah, exactly. Yep. So in that case, for our setup, by over 57.3 is equal to sine 36 degrees, right? So by is equal to 57.3 times sine 36, and then this will be a negative answer because it's moving south, and that should be around negative 33.68 meters. And the reason why it's sine is because we have here your hypotenuse, right? You have your angle. This is opposite to your angle here. This by is opposite to the angle, and so opposite over hypotenuse should give you sine. So it should be negative 33.68 meters. Let me know if you guys got that as well. You did? Okay, cool. Sounds good. For part B, the net displacement from the starting location to where the keys are buried is the vector sum r equals a plus b plus c. So our resultant vector r is the net displacement here. So we need to calculate the x component for the resultant vector. So we're just looking at rx basically, and that's going to be equal to ax plus bx plus cx, right? Because it's just taking all the different components of each one and adding them together. Because you went like this, ax, right? And then you went this way. Oops, went a little too far. This one, bx, right? Ax plus bx. And then since c is just moving south, right? There's no x component to it. Then we can just by looking at the graph, we can know that cx will be 0, right? Because you're only moving south, you're not moving west or east. So this in reality will just be 0 meters, because cx is only moving south, it's not moving at west or east. So should just be ax plus bx, right? And then we'll just add up our components, because we have AX already, 38.37 meters, and then we have BX, which was the negative 46.36 meters. So we'll just do 38.37 meters plus negative 46.36 meters, right? And then that should give us our RX. And obviously this is adding 0 meters for CX because it's only moving south. Let me know what you guys got for RX. Negative 7.99 meters, yep. There we go. RX equals negative 7.99 meters. Hopefully that makes sense for part B. Part C is very, very similar once again. It's just the y component, which is RY. So that'll just be AY plus BY plus CY. This time there's a y component for every single one because you go AY, right, to BY, and then to CY as well. So we end up with some final resultant y. So AY, we got that from part A here, which was 61.4 meters, right? And BY we calculated up here, which was negative 33.68 meters, right? Oops, there we go. And then CY was another negative 17.8 meters, right? Negative 17.8 meters there. And then that should give us our RY. Let me know what you guys got for RY as well. .92, yep, 9.92 meters. And then you can do kind of like a sanity check and see if it matches up with your picture. So we should definitely have our RX component be negative because it's in the western direction, it's in the negative X direction. So RX was negative 7.99 meters, that checks out. And then this was positive 9.92, and that makes sense since it's in the north kind of direction, right? So that's C. Now part D is saying how far does the winner have to go for the key for the starting location? So what's the magnitude of R, basically, right? So just what is R overall? Now we have RX and we have RY, right? So similar to the older problems, how can we figure out the net displacement? So what's the magnitude of R? How can we figure that out? Yep, Pythagorean theorem, right? So you take a squared plus b squared equals c squared, right? So that's your rx squared plus ry squared equals your r squared, and then you take the square root of the whole thing. So you're left with square root of rx squared plus ry squared, and then that's equal to r, right? So rx squared plus ry squared, right? Take the square root of the whole thing. So for Rx, we had negative 7.99 meters, square that. And then Ry, we had 9.92 meters, square that. And then take the square root of the whole thing when you add those two together. And that should give you your magnitude of R. And let me know what you guys got for part D. Yep, 12.74 meters is what I got as well. Now, if everyone's on the same page for part D, really part E is kind of up to you guys. It's a little bit more subjective because it kind of depends on what ruler you have and if you're using paper and pencil or an iPad and an Apple Pencil or whatever, because if I'm on an iPad, right, and I'm zoomed in like this, or if I'm zoomed out, that'll have an effect on the ratio of the lengths of R to C. So I might get different magnitudes, because if I blow it up, right, like the length of the word computed alone, if I zoom it in like this, it might be what, like an inch or two, maybe a little less, I don't know. But if I zoom it out, it's barely an inch, might be a little less if I zoom it out. So this one kind of depends on what kind of environment you guys have going on. So it just says use a ruler to determine. Yeah, go ahead. Mm-hmm. 5% difference. Um, let's see here. Let me check what I got. So we got use a ruler to compute the ratio of two magnitudes. What goes for these two? Actually, that's very, very good. I had a 20% difference the time I did it. They're not like actually like grading you on like how big of a difference you get, because like I said, some people will be using iPads, some people will be using like paper and pencil. So it kind of depends on everyone's environment. But the smaller difference you have, the better, really. So yeah, as long as you have the steps correct, like if you were able to, use a ruler or eyeball or whatever and get the magnitude of R and the magnitude of C, take the ratio of the two, and then that's by measurement, and then compare it to the ratio of the magnitudes that you have. So we had, for R, we had 12.74, and for C, what did we have for C? 17.8 meters, right? So we take the ratio, the ratio of those two, I think that's around like 0.72, 72%, right? 12.7, yeah. Yeah, exactly. So if you have that ratio, compare it to the ratio of R to C using a ruler or eyeballing it or whatever, and then take the percent difference between the two. If you don't know how to take percent difference, it's just basically percent difference is x2 minus x1 over x1, and then times 100. That'll give you the percent difference. So this could be like, let's say this x2, we can define that as the ratio of the actual measurement, or of actual magnitude, and x1 would be like the ruler ratio, right? Because if you measure it on a ruler, I think what I got for R was like 9 millimeters, and for C was 15. So if you do 9 divided by 15, you get like 60%, or 0.6, right? So all you would have to do in that case is just take, because you got 0.72 or 0.715, something like that. So you can take the ratio of the actual magnitude. Yeah, so you take like the 72 minus whatever the ratio is for your ruler measurement, and then divide it by the value of their ruler ratio measurement, and then multiply that by 100, and that's your percent difference. Okay, yeah, cool. Yeah, hopefully that makes sense. And like I said, the only reason I'm not going to do this one is just because it's kind of subjective on everyone's condition and what they're using to solve the homework. Like you said, yeah, you might not have a ruler. Other people might use their phones to measure or whatever, but it just kind of depends on how you want to do it. Well, that's fair. But yeah, if you once you get a chance to do it, it's not too bad. But hopefully that equation there kind of clears things up as to how to calculate it. And then you might want to do like a little, that's no problem. I mean, yeah, if you ever like have any issues with like remembering equations or stuff like that, then you can honestly just like search up a calculator or something for percent difference. or for standard deviation or anything like that, especially for the labs. But yeah, hopefully that comes in handy. But then I would also add for this problem, I'd also add kind of like a very, very, very brief description to indicate if there's an error or not. And so you'd basically say like, okay, if your percent difference was like 10% or something, you'd say, okay, there's a 10% difference between the measurement and the magnitude ratios. And you could say that indicates that the values are close to each other and the difference is likely due to measurement error, for example. But if you have like a huge difference, right, let's say like 60 or 70%, something like that, then you might say, okay, the values are not close together and this issue or this error might have been due to a calculation error or something like that. So the smaller your error is, the more it's due to measurement, like what ruler you use, if you're zoomed in or zoomed out on an iPad, if you can't see the number, like the number ticks on the ruler correctly or whatever. But if your error is huge, then it's more likely down to a calculation error because like using a ruler is, I mean, I guess it's a very informal way to say it, but using a ruler is pretty straightforward. But doing the calculations is a whole nother thing. So like if your error is huge, it makes more sense than that your calculations were wrong. But if your error was small, then it was probably just due down to like your eyes not being properly calibrated, and yeah, you're not messing up the measurement. But yeah, anyway, that's about it. But yeah, so that's the written homework. Usually Sundays is just the written homework, honestly. Um, if anybody else has any questions about any other like homework problems or whatever, then I might go over that. But yeah, generally Sunday is written homework, Tuesdays is quiz review, and then Wednesdays, if you have any questions about the online, about the written for that week, for any week's previous concepts, anything like that, Wednesday is an open session, and they're all from 6 to 8 p.m. on Zoom with the same link. I might change up the platform that I use, so next week I might try and use something other than Zoom. Today Zoom has been working fine. I don't think you guys had any problems so far, but the first time I used it, I had to refresh a bunch. So yeah, if it keeps going well, I might stick with it just for the sake of convenience because I don't want to change up the schedules and stuff. But if it doesn't, then I might have to change it to like, I don't know, Google Meet or Blackboard Collaborate or whatever it is. But yeah. All right. I gotcha. Okay. But yeah, all the sessions will be recorded, uploaded on Google Drive and YouTube. So, if Google Drive is down, YouTube is almost never down, and vice versa. So, yeah. Alrighty. That is all of the written homework. Does anybody have any questions about anything else? Yeah, no problem. Yeah, no problem. I'm glad to help. I'm more than happy to help with all this stuff. And yeah, I don't know if you're in the group me, but if you aren't, I would see if someone in discussion can send you a link or something. But yeah, it sounds like you're already in the group me. It's very, very quiet, a lot more quiet than it was last year. So hopefully more people be active, and I hope more people be active because are you in the hold up? I see. Actually, give me 1 second here. Let me stop the recording as well.